Yeah, I think we're going. So, seconds here. Are you guys listening to me? Amir seems frozen. Yes. Okay.
Sorry, can you see me now? Okay.
so let me. Yes, perfect. So Amir is a postdoctoral researcher at the University of Amsterdam, as well as QSoft, a quantum compute research institute in Netherlands. She was previously an intern at the Google Quantum AI and a pre-doc researcher at IBM Zurich. She holds a PhD in quantum computing from the University of KwaZulu-Natal, during which she was a recipient of Google's PhD fellowship and the Oppenheimer Memorial Trust Award. Let us all welcome our speaker.
Thanks very much. Okay, cool. Let's share the screen again. Okay, good. Yes, thanks a lot for inviting me to give the talk. And there's not too many of us, so I think we can have lots of discussion, and I would really appreciate, questions and if you have any thoughts. And yeah, I'm also not sure of everybody's background, but I think I hope that you'll be familiar with like a lot of the quantum computing language that I use, and then the machine learning stuff's actually not so important, I think, for the talk, but it's perhaps a relevant application of what I will tell you. So yeah, so this paper, well, this work came out of some research that I was doing as an intern at Google, and morphed into a paper which is now will appear in like NeurIPS, which is this classical machine learning conference that I think people seem to like a lot. And yeah, so it was in collaboration with the following people. And it's got a long title on quantum backpropagation, information reuse, and cheating measurement collapse. But hopefully these elements and these words will become a little bit clearer as I go through the slides. Okay, so in a nutshell, when I talk about quantum models, I want to just make sure we're all on the same page. So in quantum machine learning, for some reason, people seem to use these parameterized quantum circuits a lot as their models to do machine learning. And so these parameterized quantum models, I mean, they're quite straightforward in a quantum sense, right? Like you can imagine that your function, which I call f, depends on some parameters theta. So you can think of theta as like, I don't know, some vector. And these parameters in this function come to us in this form. So this function takes on this following form here, where you have some state, some initial state that is parameterized. So you can imagine maybe you start with some arbitrary initial state, you apply some parameterized operations to the state, and then you're interested in measuring some observable. And this model, like, comes up in other areas other than machine learning, right? I mean, I think also like in chemistry and things like this, when people are trying to perhaps learn some target state or so approximate some ground state energy or something like this, usually people add some parameterized operations in a circuit and then tweak them to get like a desired state or outcome. Optimization as well, like there are also these kinds of QAOA models that encode combinatorial optimization problems into the observable or something like this. And usually there's also some notion of parameterization in there and tweaking and optimizing parameters. So yeah, and then of course, like in quantum machine learning, I think in my experience, 99% of the time when somebody is doing something sort of quantum machine learning, they usually are just using this parameterized circuit here. And so, the argument is like, maybe these models are more expressive or interesting than classical neural networks, something like this. I'm not saying that this is the case, but all I'm saying is that people care a lot about these models. They seem to be quite popular in quantum computing. And
when you're learning, are you trying to learn theta or learn the observable?
Yeah, good question. So in this setting, how we think about learning is kind of training your model to learn an optimal theta. Yeah. But I mean, it's a little bit unclear, right? Because you could kind of imagine parameterizing your observable. So you can kind of put the parameters in O, and then you're kind of learning an observable there as well. But in this setting, imagine just trying to like estimate some expectation value, and you want this expectation value to be meaningful in a machine learning sense. So maybe it approximates an output label or something like this that you're trying to learn. Yeah, does that make sense? Does that make sense? Yeah. Yes, no. Okay, I can't hear. But hopefully it makes sense. If it doesn't, just feel free to ask. Yeah.
Yes, it does.
Sorry, say again. Yeah.
I was using thumbs up.
Oh,
Yes.
sorry, I can't see this. I'm so sorry. Okay, good. I can't actually see any of you. I just see my slides. So okay, good. All right. Yeah. Okay, and yes, please ask, because I think also when people talk about learning theory or learning problems, there's all different kinds of models and ways to define this, and hopefully it will become clearer when I talk about things like sample complexity and stuff like this. Okay, good. So yes, so people care a lot about these parameterized models, and since they're functions that depend on parameters, and we want to be able to find the best parameter set for our task, we're going to need to be able to optimize this function in an efficient way, right? So efficient, I'll explain exactly what kind of efficiency we're looking for. So we need to be able to optimize this function. And how do people optimize parameterized functions classically? Usually they use gradient-based methods, right? And why? Because gradient-based methods in machine learning in particular work super, super well, right? They just find sort of good optima, or minima, I should say, that kind of work well for a particular problem. So just a brief kind of interlude on classical optimization techniques with gradients. There is this algorithm called backpropagation, which I guess most people have probably already heard about, but just like very quickly, this idea of backpropagation is really just a recipe. You can think of it as a recipe to compute gradients, right? And it does it in an extremely efficient manner. And in particular with like neural networks, for example, where you can have tons and tons of parameters, like billions of parameters, backpropagation is really the reason why we're able to go to these kinds of scales with these models, because we can compute gradients of these functions with tons of parameters in an efficient manner. And yeah, so one quick mention is like, a lot of people sometimes think if you look at explicitly the function of a neural network. So if you're not familiar with how neural networks look, it's not so important. What is important is that there seems to be a lot of repetition in the calculations or redundancy in the calculations of the function, that when you write out the expressions for the gradients, you can use the chain rule to like write out the derivative with respect to every parameter. And there's a lot of like repetition and redundancy in there. And so people sometimes think, oh, backpropagation efficiency just comes from the chain rule because there's a lot of repetition and redundancy. But it's a little bit more sophisticated than that. It's a little bit of like a sort of dynamic programming approach where information is stored and reused in the middle as you like compute the function. Intermediate information is stored and reused in a very clever way that allows you to compute gradients much more efficiently. So this is like this is the key to backpropagation. Okay, so yes, okay, this is just like my little depiction of deep learning. And all I want to say here is that even though we knew about like perceptron models, neural networks for a long time, it was really up until we could train them efficiently with algorithms like backpropagation that created all this exciting new research of deep learning. And now we're in this large language model regime where I think we even have trillions of parameters in a model, right? So this is really only possible because we can train these models at scale. Okay, so what is this amazing scaling that I keep talking about of backpropagation? And yeah, let's spend a moment here. So if you're going to take anything away from what I tell you today, I think this is the best thing, the best slide, or the best thing to kind of remember. So it's a very general kind of definition. So when I talk about backpropagation scaling of resources, imagine that you have some parameterized function, right? So f of theta is any, you can think of it as any kind of classical parameterized function, maybe like a neural network, for example. And now theta, there are many parameters in your model, right? So there are m parameters in your model. So you can think of theta as like some n-dimensional vector, something very high dimensional. What backpropagation wants or does is it says, okay, I'll estimate the gradient of this function, right? So the gradient now will contain m entries. You can think of it as a m-dimensional vector as well. And you want to estimate this full gradient vector with some constant precision. What backpropagation gives you is it says, okay, the time that it takes me to compute this full gradient vector is less than or equal to the time it takes to just run the function once times some small constant here. So C1 and C2 are just small constants. So if you think about that for a second, that is actually quite amazing, right? Like, because you would think naively the time it would take to compute every derivative would kind of, require you to compute the function once at least for every derivative component, right? Naively, this is like maybe how you would do it. But it's saying that actually computing the full gradient vector, which is super, high dimensional, is tons of parameters in there, costs me the same amount of time that it would just cost me to run my function once, roughly. And the same is true for memory. So this is really quite cool. Okay, so this is a relative scaling of resources, right? So this is saying that the time to compute a function is roughly the same as the time to compute the gradient. And in particular for like neural networks, which are our leading classical machine learning models, these constants are known to be quite small. They're like a factor of 2 or 3. Maybe. So we can kind of actually think of these things as proportional. Okay, is that clear? Because I think that's quite important. And I know I haven't said what constitutes time and memory, and of course it depends on the type of device and the type of native operations you assume to have in your system. But this is just the main high level picture. Okay, and then of course now for us the next extension or the next question is like, okay, well, can we achieve this beautiful backpropagation scaling for quantum models, and in particular these parameterized quantum models that I showed you in the beginning of the talk, right? These are, when I say anything is like a quantum model, you can think of these parameterized functions or these parameterized expectation values, right? So can we achieve this this same nice relative scaling? And even if we relax this assumption that C1 and C2 need to be constants, maybe they can have some sort of vague dependence on the number of parameters m. Maybe we can have like some polylogarithmic dependence on n, right? Even if we relax that, can we get close to this relative scaling? And I'll point out immediately that no gradient methods to compute derivatives of these parameterized circuits achieve this scaling, right? So no current gradient methods in literature get close to this kind of relative overhead here. Okay, so why, right? Let's spend a moment on like how do the gradients look of these circuits, and then we can discuss like what time and memory actually looks like for these parameterized functions that I'm talking about. Okay, so there is a little a straightforward nuance actually here, right? So imagine now you've got like this is like a very simple, elementary school example, but I think it's good for illustration. So imagine you've just got like one qubit in your circuit or your model, right? And to create your parameterized state, you're just going to apply one parameterized operation. So just like some rotation about about an axis, and it's parameterized by theta. And theta now is just, you can think of it as a scalar, so it's like one dimensional, right? So there's just one parameter in the model. We can actually just draw the circuit. Yeah. Okay, so we know that like we can actually by hand write down the derivative of this parameterized state. It's quite easy, right? You just drop this like minus ix here. And if we wanted to, let's say, measure some observable, let's say this Z operator, then we can actually write our function, our parameterized function, explicitly like this, right? It takes on a very simple form. And so this is we can think of this as like our parameterized model. And now we're interested in estimating the gradient of this thing, right? So the gradient with respect to, sorry, my lights went off. Okay, the gradient with respect to the parameter, the single parameter theta. If you stare at long, you can kind of use a product rule and then simplify this. And in the simplified setting, let's just say we set the parameter to 0 to evaluate the gradient. And what I want to show you is that it just kind of reduces to estimating this expectation value here. Okay, so we have this derivative. We set the parameter to 0 to evaluate the gradient at 0. And yeah, we have this expectation value. Now, when we have two parameters in our model, let's say now instead of just doing an X rotation, we also do a Y rotation parameterized by a different angle. So now we've got two parameters, theta1 and theta2. Then we can do exactly the same thing, right? We can write out explicitly the gradient with respect to each parameter, with respect to each component. And we get, again, like, these expressions. And let's say we want to simplify it and set the parameters to 0 and evaluate the gradient components. then what I want to show you is that even in the simplified setting, when you set these parameters to 0, this corresponds to estimating now 2 different expectation values with respect to operators that don't necessarily commute, right? And so you can kind of get a sense for why estimating gradients of these models of this form is not so straightforward, because like estimating, let's say, m gradient components kind of corresponds to estimating m expectation values, right? And these expectation values are with respect to operators that don't necessarily commute. So it's not so straightforward. And also reusing information is not so easy, because as we know, when we try to estimate these expectation values, we have to sample and we destroy our quantum information, right? So this is why it's not necessarily so straightforward. Whereas with neural networks and classical functions, you can kind of reuse information, store it, no problem, you know? Okay. All right, so let's talk about our cost model now. Okay, so in the quantum sense, now I will talk about like how we account for cost in terms of time, right? So you can imagine that you do like these parameterized operations now, and these parameterized operations are just call them like some arbitrary unitary uj, and each uj depends on parameter theta j, okay? And so if I have m parameters in my model that I want to apply to some initial state, then I can think about it as like this product here, this product of UJs where J runs from like 1 to M. So there are M parameterized operations. And I just kind of, use this bad notation of concisely summarizing all these M operations as U theta. Okay, so this U theta here has basically M parameterized operations. So in this cost model, I'm saying that each UJ and its inverse just costs me one. Yes.
Yeah,
sure.
Sorry, we find your slide maybe stuck at page 9, so it does not change.
Okay. 39. So do you see the parameterized unitary?
Yes.
Okay, good. Then hopefully.
But only one parameter.
Then it's still on one parameter?
Yeah,
Yes.
still just on theta.
Okay, hang on. Do you see this highlighted U theta?
No.
No? Oh, okay, hold on. Let me stop sharing and then I will. Try again. Oh, so it got stuck on the one parameter example?
Yes. On slide 9.
That's not good. Okay.
But
okay, good.
That slide disappeared now.
Yes, I stopped. I'm gonna try sharing again. Okay. All right, so it stopped at slide 9, so that's not good. Okay, so do you see now slide 10?
I don't see anything. Just black.
This is very strange. Okay, hang on 1 second. I will. Okay, hopefully this should be better. I've changed internet connections. Can you see now slide 10?
Just keep black.
Hello?
Hello?
I can't, but I'm not sure if it's because of my connection or not.
I just see black.
Okay, now I cannot hear you.
Can you hear me?
I can hear you.
Okay.
I think she disconnected to reconnect again.
Mm-hmm. See?
Okay, I'm back. I'm terribly sorry about about this connection. Hopefully you can hear me now and see me now.
I can hear you, but not see you.
I can.
You
Yeah,
can hear me but
same
not see me.
here.
Okay, let's try share the slides though. At least that should be working better now. Do you see slide 10?
I see no slides.
No.
It's black.
No, no, why? I don't understand. This is very strange.
Wonder what happened.
Did you ever experience this problem before?
And no, it's the first time.
Okay, I think the only thing else I can do is maybe try a different browser. So let me try that quickly.
Okay.
Okay, I'll be right back. Sorry about that.
No problem.
Andrew, I think maybe you can stop the recording now.
But then I would have to restart again, right?
Yes, it's up
I
to
can
you.
cut.
You have to. Yeah.
No. I think I can just cut this part off when I'm uploading the video, and I think we'll be fine.
Okay. Up to how you process it. Okay, sure.
Mhm.
Okay.
Now I can see you.
Better can see you.
Okay, great. Because now I'm using the Teams app, so hopefully, hopefully this helps a little bit more. Okay, and the sharing is faster. Let's see. Okay, please. I hope you can see slide 10.
Yes.
Yes.
Okay,
Perfect.
great. Okay, great. Yes, and don't worry about time. I think because I planned a shorter talk, so hopefully I won't go over time. Okay, good. So yes, let's maybe speed up this part. Okay, so the whole idea was like computed gradients, if you remember, of like these parameterized functions. And all I wanted to say was when we kind of simplify this task of estimating the gradients with respect to every parameter, it kind of reduces in a sense to estimating expectation values, different expectation values with respect to operators that don't necessarily compute. Okay. So if we have like a ton of parameters in this parameterized circuit and we want to compute the gradients with respect to every one of them, you can kind of form an intuition as to why this is like sort of a difficult task, right? Because it's not easy to reuse information because we kind of have to sample to compute expectation values. And we can't like really do this efficiently because we can't observe this together to kind of estimate things efficiently, right? So this task of estimating lots of gradient components is very similar to the task of estimating lots of expectation values. Okay. All right, good. So now we can talk about the cost model in terms of and here is what I was talking about with these parameterized operations now. So you can imagine like you have some sort of arbitrary unitary that you apply all through your circuit, and they depend on some parameters. So each uj depends on a parameter theta j. If I want to apply m of these parameterized operations, then I can just think about it as a product, from like m of these. And in this cost model, you can think of each uj that you apply, each parameterized operation, and its inverse that as unit cost. So every time I apply one of these uj's and its inverse, this will cost me 1 unit of computational time. Okay, so if I want to apply, m of these operations, which I, concisely write as just u theta, it's like really bad notation, but just imagine this has m parameterized operations in it. Let's say the initial state is just the all 0 state, and I want to apply, u theta to it. So that means I'm applying m parameterized operations. So to create this parameterized state in my cost model, this would just cost me like roughly m units of computational time, right? Pretty straightforward. Okay, and so my function is then like, remember we're interested in measuring some observable, and I'm applying this parameterized operations to my initial state. So to estimate this expectation value here in this cost model setup, this would cost me also roughly m, right? Because like these u's and the u daggers, each operation in there costs me just 1 unit, and there's m of them. But usually we have to sample to get this expectation value, right? So maybe there's like some notion of sampling error like epsilon or something like that. But this is not so important for the cost model. What is important is the scaling in the number of parameters that we have. So this is how much, naively it would cost me to estimate my function f of theta if I have a parameterized circuit. Okay, now to compute gradients or derivatives, if I want to, let's say compute the derivative of my function with respect to one parameter, which I call theta k, so the kth parameter, I can explicitly write this out, and you can just take my word for it that it's can be expressed like this, right? Where this is an expectation value as well, that kind of almost looks the same as my function, except there's a partial derivative in here with respect to the kth parameter, right? Okay, so this thing here, if you look at it closely, would also actually cost me m units of computational time, because there's like m parameterized unitary operations occurring here. Okay, but the catch, of course, in this like gradient cost model is that this is just for a single component, right? So here we're just estimating the derivative with respect to one parameter. And so if I wanted the derivative with respect to all m parameters, then this would give me a cost that scales roughly like m squared, right? Because it's m for one parameter, and then there are m parameters. So this is like quadratically in m. So if we think about this relative scaling in resources that I mentioned earlier, this is saying that the time that it takes to compute the gradient is m squared, which we can think of as like m times the time it takes to compute the function. Because the time it takes to compute the function is like linear in m, and the time it takes to compute the gradient is quadratic in m. So we have like an m times the time to compute the function. And this is not good, right? Because if you remember what we want, classically, these things are roughly equal. There's no factor of m here. We want to reduce this factor of m to something like polylogarithmic in m, or maybe even constant. So this is not so good when we compare to classical models. And you might think, okay, well, it's, this quadratic to linear difference is like not such a big deal. But actually, it is quite a big deal in practice. In practice, if we have this quadratic scaling in the number of parameters, then we will not be able to compete with things like neural networks and stuff like that. We won't be able to scale our models up to a reasonable size. So in this picture is an illustration of why. So on the x-axis, you can imagine like this is how much time you have to train your model or optimize your model. And if you, let's say, have a day to optimize your models, that's quite a significant amount of time. If you do not have backpropagation available to you, but you use methods like the parameter shift rule, which compute gradients with this bad quadratic scaling in the number of parameters, you would only be able to train a model with up to 9,000 parameters. Whereas if you had backpropagation, you can already train a model that is up into the millions of parameters. So you can kind of get a sense for why we really need to do better in this optimization picture. Okay, good. So now I can just tell you some of the results of what we found, like in this question of can we ever achieve this wonderful backpropagation scaling. So there's a couple of things that you can immediately say depending on the settings that you're in. So the first setting you can imagine is your input state is entirely known to you, right? So you're just given, let's say, some input state that like the all zero state or something else you know how to construct, and then you apply your parameterized operations to them to create your parameterized state. But a more general setting you can imagine is you don't know what your input state is. You're just given some arbitrary psi, like some arbitrary input state, and then you apply some parameterized operations to it. And then the other settings you can imagine to have is perhaps you can only make single copy measurements to your system. So you can only make single copy measurements to single copies at a time. Or more generally, maybe you are allowed to make measurements to a tensor product of copies, right? So you can do like a big measurement over a number of copies at once. Okay, so these are these kinds of like different settings you can imagine. And already we can say when we are in the scenario where the input state is entirely unknown to us, it's just given to us, and we can only measure single copies at a time, which realistically I think in the lab, like this is probably like the most useful setting, right? Because you don't want to make assumptions about your input state. And usually I think it's easiest to just make measurements to single copies at a time. So this is like quite a practical scenario. Unfortunately, in this scenario, we can already use some results that tell us that backpropagation is just not possible to obtain in the general sense. And the results come actually from a sample complexity lower bound of this paper here. And how you can see this is if you take in your circuit all possible parameterized operations as Pauli operations, then this task kind of reduces to this task of estimating expectation value with respect to Pauli operations or Pauli operators. And in principle, like, this requires a certain amount of samples, translates to a cost model, like, and if you plug it back into our cost model, it translates into this like bad quadratic scaling in the number of parameters that we don't want to see. So we still have like m times the time it takes to compute the function. And we want this to be sort of constant or polylogarithmic. So this is a bit sad. Yeah, I guess a bit of a negative result. But then, one can then try and say, okay, well, what if I relax this assumption that my input state is entirely unknown? Maybe I know how to construct it, or maybe even maybe even I can say it's promised to come from a circuit of like polynomial complexity or something like this. There in the paper, we kind of also show that there are computational arguments that rule out backpropagation scaling in general. So I don't want to spend some time on why this is the case. If we have time afterwards and people are interested, then we can kind of go into it. But basically what I want to say is that even if your input state is like guaranteed to come from a circuit of a reasonable depth, you can still like show that it should be hard to get backpropagation scaling in general. And this like argument uses like classical shadows and some pseudo-random arguments to show this like computational hardness stuff. Okay, so let's actually just quickly skip over that. Okay, so what I'm saying that to sum up, like even if your input state is known or unknown, if you only have the ability to measure single copies at a time, this backpropagation scaling seems rather unlikely. In this scenario, we know it's not possible in general, and in this scenario, it seems computationally unfeasible. Okay, so the last thing we can do, of course, is now wonder what happens when we go to the setting of allowing for multi-copy access, right? So measurement to multiple copies at a time. And intuitively, I just want to highlight a couple of things again. So why is it not straightforward when we have single copies, right? Especially if we look at like the structure of our function and the structure of our gradient components, there is so much repeated in here, right? There, you remember these U's are like kind of a product of M parameterized operations and pop up here and in here. So you should be able, if you could reuse intermediate information in your circuit, you should be able to compute gradients in a much more efficient manner, right? Because you can kind of use information from computing the function to compute gradient components here, if we could store information efficiently. But we can't do that when we only have measurements, when we can only make measurements to single copies, because every time our circuit here, we kind of lose all the information, right? And so the intuition of when we allow multiple copies of our model, we have this idea of like quantum memory, people call it. The intuition of why we can perhaps do better here is because when we have multiple copies in memory, we can design measurements in a little bit of a more clever way. We can design measurements such that we can get some information out, of our function and perhaps our gradient, and we don't necessarily destroy all our quantum information. So we can design measurements so we can get some information out, and we can reuse our copies in memory thereafter again to do more measurements, right? So if we have multiple copies, we can in a sense design measurements in a gentle fashion that they don't disturb our quantum information, and so we can reuse them to do things more efficiently. And this idea is, inspired by a lot of success of having multiple copies of your state at a time and being able to measure over a product, and then you can sort of show that there are separations that exist in what you can do in this multi-copy setting than if you could not. Okay, so the first thing that's nice to notice is that in a special case where you imagine all your parameterized operations as just Pauli's, so they're parameterized Pauli operations, then if you have the ability to measure multiple copies at a time, you can actually achieve this backpropagation scaling in time. So this is efficient, and this is like the first nice thing. So this is positive, right? This is indicative of, okay, maybe we're on the right track. If we have multiple copies now, and in the special case where we just have Pauli's, we can do things nicely. But unfortunately, when we move a little bit away from this restricted case of just thinking about Pauli operations and evaluating the gradients at a specific point, things get harder. The scheme that we use to create this efficiency, which comes from this paper, doesn't work anymore. And so you have to then is there some sort of deeper barrier here? How hard is this problem of achieving this particular efficiency for these gradients? And indeed, there is. There's actually a straightforward connection or reduction to this problem of shadow tomography. So if you haven't heard of this shadow tomography problem, I'll just spend literally I think it's quite a beautiful problem and very well studied now in the literature. And I think it was first proposed by Scott Aronson. And the shadow tomography protocol, the shadow tomography problem just goes like this. Right? So imagine now we're just dealing with two outcome measurements, right? So there's some class of measurements, and they're just two outcome measurements. And now I'm given a certain amount of copies of my state, some quantum state psi. So I'm given a number of copies of it. And now I'm interested in making some known measurements, and I'll call these measurements like E1 to EM, right? So M can be quite large. The task of shadow tomography says that I want to come up with estimates that are close to these expectation values that I'm interested in, right, with respect to all of these E's. And I want to do this where I use a number of copies that is as small as possible, right? So I want to estimate essentially a lot of expectation values with respect to a state, but I want to do this with as few copies as possible. And if you remember what I said at the beginning, the task of estimating gradients is very, very similar to this task of estimating, expectation values. And so what we know is that actually, there is a reduction here. And if you find an algorithm can estimate gradient components with a specific precision and a certain runtime, you can actually show that you would solve the shadow tomography problem with respect to a particular class of observables in the same runtime. So what is that saying? That's saying that the gradient problem is at least as hard as the shadow tomography problem. And how we do this reduction is we define this general model, which we call a quantum neural network. It looks very similar to everything I've talked about earlier. Okay, so now the last thing that I will say is, well, if there is this connection between shadow tomography and gradients, is there anything from shadow tomography that we can borrow to perhaps make a gradient algorithm like backpropagation, something efficient? And this is exactly what we do. So we propose this sort of quantum efficient backpropagation algorithm using techniques from shadow tomography. So yes, so the details here are not so important. What is important is that using some results from shadow tomography, like sample complexity and so on, we can plug it into our cost model to get a very general algorithm that gives us something in line with this backpropagation scaling. We get this this m down to something polylogarithmic in m, which I think is the first proposal to achieve this. Okay, but there's a huge catch, in our approach, and the huge catch is that our protocol requires memory that scales exponentially in the system size, and of course, classical neural networks, classical backpropagation doesn't have this problem. So this is a problem, and this is in general something one cannot get rid of. So how the algorithm works, I'll just give you a snapshot, and then we can discuss. It's actually quite beautiful. So it borrows from two techniques. So one is this online learning, again proposed by Scott, and the other is this this idea of something called quantum threshold search, which is proposed in the second paper here. So how the algorithm works is it says, okay, I've got some copies of my state in memory. So these are these rows here. And then I'm going to apply parameterized operations to them. And then I can do something called a threshold check. And this threshold check basically kind of checks if my expectation value I want to estimate is close to an estimate that I have offline classically, right? And if these things are close, then I don't destroy my copies in memory and I can proceed with the algorithm. But if these things are far apart, then I kind of have to measure to get an accurate estimate of the expectation value I want, and then I have to reuse a fresh batch of copies. So how do I do this threshold check? And this is where the exponential classical memory comes into play. So there is a sigma here, which you can think of as a guess for your state row, which is a classical description of a density matrix. This is why this is expensive. We literally have a classical description of a density matrix in memory here, right? So this is like a DN matrix. And we use this guess to do these threshold checks. So I have this like density matrix in my classical computer, and I can design a measurement that kind of compares like my classical description of my expectation value to my quantum description in a very gentle way. And if these things are close, then I just proceed with my classical description. And then I can kind of do this, a certain number of times, and I can bound how many mistakes I make, how many copies I will need to show that in a reasonable sense, like with enough probability, we can eventually get all the gradient components out that we're interested in. So yeah, I hope that kind of intuitively at least makes sense. And the reason that this succeeds is really because we can have multiple copies in memory. So this idea of having multiple copies in memory is quite powerful. Right? Okay, so here's like the takeaways again. Okay, so if we are in this setting where we just have single copies and we know our input state, there are sort of computational arguments that we outline in the paper that show that in general, backpropagation scaling should not be possible. This like nice relative overhead is not achievable. In the case where your input state is unknown and you just have single copy measurements, we know that it is impossible from an information theory argument that in general we cannot achieve backpropagation scaling. And then in the multi-copy case, for either where your state is known or unknown, we can do things in a time-efficient manner thanks to this algorithm that we propose that uses like gentle measurements at each step. But unfortunately, like the memory is super expensive, and in general, if you use shadow tomography protocols, there is no way to get around this. So this is this is the story. And I think there are a ton of interesting open questions that can be, investigated. So the first is, of course, the hardest one is like, okay, is there actually an efficient computational scheme for gradients? Maybe there is another protocol outside of what exists with shadow tomography to solve this problem. But perhaps, more reasonably, maybe there is a special restricted class of models that can achieve this nice scaling and it's expressive or interesting in some way. Or maybe it is just time that we look at something else other than these parameterized quantum circuits, right? Maybe this is just something that will not scale, and maybe we need cleverer ideas, especially in this quantum machine learning environment. Or perhaps there are also smarter ways for optimization, right? A lot of people ask about what about gradient-free optimizers? Everything I've talked about is computing gradients, but like in general, I have not seen a good proposal for a gradient-free optimizer that achieves a reasonable, in a reasonable cost model, a good scaling. So yes, I think that's everything I wanted to say. I'm really sorry about the technical difficulties. I hope it didn't like disrupt things too much, and you're still able to take away like the main messages here. And I hope this was interesting for you. And I'm happy to like discuss and take questions.
Yeah, thank you very much. It was a very nice talk.
Good.
Don't worry about the technical problems in the beginning. It's completely fine. And when I upload things, I'll cut it off. And
okay, great.
As you said, now we can open for questions. I think we have a question already. No, I think perhaps a like.
That's good.
So does the audience has any questions?
Maybe I have
well,
one.
they think. Okay, so please go.
Yeah, so is the multiple access of memory easy to implement, or it's just some theoretical possibility?
Okay. So yes, let's go here. Yes, this is definitely to implement as long as your number of qubits is not too large, right? Because we have to store this classical density matrix. You can imagine, when you're trying to store already like up to 10 qubits in memory classically, this matrix becomes very large. But it is explicit, and it is definitely something concrete. So we actually give like a way to efficiently implement these threshold checks. The observables are like very clearly defined. So indeed, it is an explicit algorithm, and it is something you can actually go ahead and implement. I don't know though, like how easy it is to do measurements like realistically in the lab, multiple copies. I believe this is very hard. So maybe this is a blocker. But like if you wanted to, let's say, simulate this algorithm classically with a reasonable amount of qubits and stuff like this, you can definitely do that.
It's like a shadow tomography. You just have access to the multiple copy, but you store them in classical computer. Is that right?
Yeah, exactly.
Okay, I see. Thank you.
Thanks.
By the way, you mentioned that you have this memory problem, right? And I think kind of towards the middle of the presentation, you show two scalings, one in respect to time and another in respect to memory. So this memory problem is related to the second one that you showed to us?
Exactly, yeah, that's right. Let's see, where is scaling statement? It's right at the beginning. Yes, that's exactly right. So I actually kind of, mostly speak about time complexity because this one is at the moment like nothing achieves this. But yeah, you're right. So the exponential memory, this requirement will then be violated, right? Because the memory to compute expectation values of the function, you don't need a classical density matrix to do this. You can just sample from your circuit a certain number of times and just use like however many qubits you have in your circuit. This will constitute your memory. So the fact that for this gradient protocol here on this side to compute the function, we need this density matrix stored on a classical computer, yeah, then this relationship doesn't hold.
Okay. Makes sense.
Yeah, so the key and the hope
Yeah.
is to try and get this for both, I guess. But it's of course not so straightforward. So if you're just dealing with like a model with Pauli operators and you're evaluating the gradients at a specific point, like let's say you set the parameters to 0, then you can actually show that this is achievable. But this is a very simplified setting, a very unique setting, and when you generalize it, it doesn't hold anymore.
Do you have any guesses on or how to overcome this right now? I'm not sure if you guys are working on this.
Yeah, so there was like a sort of paper that came out after us that looks at like so if you have operations in your circuit that commute, you can kind of group them together and then like measure in a common basis, right? So you can like do things a little bit more efficiently. So there is a paper that came out by people at Xanadu that kind of analyzed this trade-off, like where if you have operations that commute, so you can nicely like get gradient scaling, how efficient and interesting are these models, right? Because if everything commutes, perhaps it's classically simulatable, and then it's like not so interesting. But they kind of analyze how much I think non-commuting behavior and how much resources you need to compute like gradients and this interplay between the two. But how I would imagine like maybe overcoming this is perhaps coming up with a cleverer way to do gradient descent with these models. So there is a paper in the works with some people at Berkeley that are looking at something called coordinate descent, where imagine, everything I've been talking about is trying to estimate this full gradient vector, but maybe you don't need this full gradient vector. Maybe just the largest coordinate in this gradient vector is enough to tell you how to change the parameters in your model so that you get to like a good space for your thetas, and you have a good output. So there are maybe more sophisticated ways to do optimization. Like this coordinate descent is one idea. Another idea is maybe like using the sign integration of the gradient and not the actual values. This is also shown to work classically in machine learning. So yeah, I think maybe this is like something cool that one could try.
Okay, very interesting. Okay, thank you.
Yeah, sure. Thank you.
Do we have more questions?
Yeah, maybe I have one more question. So to calculate the gradient, do you need to know the form of the f theta?
You mean the yeah.
So you are analyzing the circuit in the fixed form, right? So all the gate circuit are fixed. So it's not like you will change the gate or operator during the simulation. It's all fixed. So you already know their form exactly. So you just want to change the theta at different parameter. Do I understand correctly?
Yes, that's right. Yeah, exactly.
So if we are applying them to the adaptive VQE, for example, some people will like change the operators during the simulation, adding more gate or double gate. Do you think it's still possible to apply this technique?
Yes, I think that would probably be even harder, right? Like because if your model is like constantly changing, I guess this is just saying for a fixed model, these relationships should hold. And if your model is constantly changing and maybe you have more parameters in there, this might even be even harder, or maybe this is not the correct formulation of quantifying resources in this way. So Yeah, I think it maybe that's even more general, right? So it's probably even harder. Yeah.
I see. So do you estimate how large your method can be applied to, for example, how many parameters is possible for your
Yeah,
case?
good question. There was like a classical simulation that I think we could do up to if you make like if you make some assumptions about your input state, like maybe it's you can store it efficiently. You can have an efficient description of it on your classical computer. Then you maybe can do some like simulations up to, I don't know, I think maybe like 50 qubits or something like this. But it's for a very like simplified setting, and and not that many parameters, because otherwise things become quite expensive quite quickly. So yeah, I think trying to implement this on a practically relevant problem is not going to give us anything interesting yet. I think we really have to find a better way to handle this classic memory storage problem, and maybe, for example, things like tensor networks and classical descriptions of a particular state can help.
I see. Yeah, I think this is very interesting work, and yeah, to implement larger system, yeah, you have to have special treating of the state description. Yeah. Okay. Thank you very much for the nice talk.
Oh, thank you. Thanks for the question. Maybe I can also stop sharing so I can see you guys.
I have two kind of naive questions here, if you could. The
sure.
first one is that you start things by saying by kind of comparing the time scaling in regards to this parameterized function and some estimate. How do you do this estimate?
Yes, good question. So this is where the importance of the density matrix storage often comes in. So imagine, and this is what I think this is the whole idea of something called online learning. So imagine you have some guess for your state that you hold in classical memory, right? So we call this a hypothesis state. Then you can use this guess because you know your memory operators that you want to make. You know, it's like EI, these measurements that you want to do in your model. They're given to you. Use classical description. Let's call this thing sigma, right? This classical hypothesis state. You can use sigma to compute the expectation value with respect to the measurement you want to make, right? So you can compute like trace sigma EI. Yeah? So you have an estimate for your expectation value, but you don't know if this estimate is good or not, right? So what you can do, if you have multiple copies of your actual state in memory, you can design a measurement that checks in a very gentle manner your estimate that you have using your sigma, and like sort of it computes an estimate of the expectation value and these so the true expectation value, your estimated expectation value, these can be checked in a gentle fashion, whether they're close or whether they're far. And this is exactly this protocol proposed by like Ryan O'Donnell and a few others. So they discuss it there, like why this check can happen and how many times you will be far apart. So if you're far apart, then you kind of have to destroy your copies in memory and actually do a destructive movement, get information out. But if you're close, then that's great. You can just use your estimate, your classical estimate, and you can like proceed with the algorithm. Yeah.
Okay, I see. The second one is about the threshold check. How is it done? It's using like some classical threshold gates like that we have for classes like TC0 or?
Oh no, yeah, so this is exactly the same thing that I described, right? This threshold check is like checking the estimate against like the true, and how this is actually done is kind of interesting. So yeah, so you can kind of show that indeed, like you can design a measurement that does this the check in a gentle fashion, and gentle means like if you look at the states after measurement, they're close in trace distance, right? So they're sort of reasonably undisturbed. But I think like the more interesting thing is how do you then go and like, if you're wrong, how do you then go and update your classical density matrix, right? How do you do this? And this is all, I think, outlined in this paper by Ryan O'Donnell and others. And it gets a little bit technical in that, like, you make an assumption about the state, and you then like write it as a Gibbs state, and then like depending on your estimate value, you kind of update the Hamiltonian in a certain way. And yeah, I think it gets a little bit technical, and I actually don't remember the details of how the threshold of check operator happens. I'm not sure if you define it explicitly. I'll have to go and check. But everything is essentially established in the paper, and we just kind of borrow the results. Yeah, the only thing different that we do is we apply parameterized operations before each threshold check again, so that we can compute gradients. But yeah. Sorry, I don't think that answers your question. But it's in the Ryan O'Donnell paper. Yeah.
Okay. Thank you very much. I think we don't have more questions. So if that's it, let me thank you again for accepting our invitation.
Sorry.
And give us a very nice talk. Huh? Oh, I was fooled.
No, thank you very much for inviting me. And yeah, I'm really sorry again about the technical glitches, but thanks a lot. I enjoyed it. Yeah.
Sure.
Good, cool.
Ming Chen, do you want to say something?
Yeah, sure. I just want to make a final question. So when you say storing the density matrix in the memory, do you need to store them like element wise accurate, or it's just as you discuss some threshold for each element is fine? So I'm just want to check this point.
Yeah, exactly. So I think like the way the analysis in the Ryan O'Donnell paper is done is like, or actually even Scott's paper, is that indeed you have a explicit density matrix description. So element wise, you have everything. But it's like a really interesting question you ask, because I think there could be some work there that like investigates, okay, what if I don't have the full description, but I have maybe some efficient classical description? Maybe not every single element, but maybe, you know, like some information about it. Can I still, you know, quantify the error even, you know, I don't have a description, and maybe this is still reasonable? I think this is like an interesting question. Yeah.
Yeah, I see. Okay. Yeah, it's really nice. Thank you.
Thanks.
Okay. Okay, now let me wait a little bit more to see if anyone will think about something else.
So will you guys all be at QIP then, because it's like right near you, right?
Well, we'll be here, but I'm not sure. I'm not sure about the people that are going to be at QIP.
Okay.
Are you coming?
I don't know. We'll see if the work gets in, but also it's a little bit tricky for me because it's during like holiday times where I was planning to visit my family in South Africa, and then to go to Taipei is like quite far from there. So I'm not sure. Yeah, we'll see.
Okay. Okay, I think we wait a good enough time. So cool. Let me stop the recording.